Hello and welcome to the Worldwide Center of Mathematics Advanced Knowledge Problem of the Week. This week we want to evaluate this, but we want to use polar coordinates, which is actually a fairly easy way. You just need a clever trick to evaluate this integral. So looking at this, there's no real U-substitution, and even if there was some trick you knew, the question says do it in polar coordinates. So we're going to massage this a little bit and get polar coordinates. So let's look at this expression, which we'll call R. R expression. R, yeah. So we have something that's we're evaluating something on every kind of on every positive x value, and we're summing that up, which is what an integral is. And if you recall, for polar coordinates, we want to instead of take slivers of slivers of our Euclidean grid, we want to take slivers of this polar grid. So I don't know if that made it any easier or harder to see what we have to do. But it's always good to think just by definitions initially. So by definition, we want to take something, we want to put something on a grid and then convert that to a polar grid. So this is not on a grid. This is on, it's not on a Euclidean grid yet. This is being evaluated on just slivers of x. That's the dx. We want to almost force this into a grid. So what we're going to do is we notice that we can just write this that way. Just turn it on its side. It's the same function. And so now we can square it. So what we're doing here is we partition our space, which is this region in the xy plane. We partition our space, and we know that on each little tile, if you will, of dx, dy length, we have a value of twice what we're getting at. So now we can simplify this and put it simply into a polar form. So now we can easily flip this into polar coordinates, and without getting into any technicalities of why this is, we know that dx dy is equal to r d theta, and x squared plus y squared is equal to r. So now we have everything in terms of r and theta, which are the polar metrics that we're going to be using. So rewriting that, so yeah, you maybe picked up on my mistake. X squared plus y squared is equal to r squared, not just r. So this expression here becomes this expression here. We have our grid, if you will, that we're taking values of e to the r squared. So we're going to evaluate this r component and then evaluate the theta component, as you would with nested integrals. So in order to evaluate what we have now in polar form, which, just to clear things up, we have, instead of x and y both going from 0 to infinity, we now have r going from 0 to infinity and theta sweeping across an angle of pi over 2. So same region, different notation. Moving on. So in order to actually evaluate this, we're going to use U-Substitution, letting u equal negative r squared, and then taking a derivative with respect to r, we get negative 2r dr. And to make it mesh well with what we have here, we just move the negative 2 over, so we have r dr is equal to something du. So now we can just put that in and go ahead and evaluate our first iterated integral. So I've just put in our u's, and reminder, we're going to be evaluating this. And it's going from 0 to negative infinity, because when u equals negative r squared, r goes to infinity, it's going to be going to negative infinity instead. So we can pull out this constant, which we'll do later. The integral of e to the u is just e to the u, and we're evaluating from 0 to infinity, so writing that all down. And we're going to take the upper limit minus the lower limit. The upper limit is just going to be 0 because we're taking 1 over e to the infinity, basically. And that's 0. And we're then going to subtract the lower bound for when acted on by e to the u, so e to the 0, which is just 1. So we have 0 minus 1, so that's negative 1 times negative 1/2, which is positive 1/2. And again, we can take out this constant, and since this is just 1, we're just going to subtract these two, the two limits, because this is going to integrate to theta, evaluated from pi over 2 to 0, and that is just going to yield pi over 2, and again we're dividing that by 2. So what we get is pi over 4. And remember, this is just r squared here, so since r squared is pi over 4 and r is greater than or equal to 0, then r is going to be root pi over 2, not negative root pi over 2, just root pi over 2. So thank you for watching. This was a little Calculus 3, a fairly tough problem. You have to use some tricks to figure it out. But if you're interested in getting more rigorous instruction on some ideas mentioned in this video, then check out our Calculus 3 textbook, which we have on our store, which you can find a link to after this video. You can also find links to a playlist of more problems of the week, or to subscribe to our YouTube channel. Thank you for watching, and have a good day.